So in Chapter 6, what we're going to do is, once we have the formula for a compound, we want to try to draw pictures of it so that we can see how molecules interact with one another, because where we're heading is to understand properties of reactions, so how compounds and atoms can interact with one another. So in summary, we're going to kind of be doing 6 and parts of 7 at the same time. Today, what I wanted to do with you, if we had met, is to do Chapter 6, which is to draw what are called two-dimensional pictures, Lewis structures, and then in Chapter 7 is going to be to look at what the molecules really look like. In other words, their three-dimensional shape. So we can do very easily, just in this little video, the mechanics and the steps of how you go about drawing a two-dimensional picture, which will make all of our drawings of our molecules look as if they're just flat molecules, and of course they aren't. Everything projects into 3 dimensions. But we at least have a picture then of how it is exactly that the elements are combining together in order to form compounds. And so in lab, you guys have been writing formulas and names for 2 types of compounds, ionic and covalent. And so those are the 2 major types of chemical bonds that we have. So in these pictures, just a couple of definitions or information here, that what you'll be doing is, in a Lewis dot structure, is that we're going to be using the chemical symbol of that element to represent the nucleus and all of the core electrons. It's only going to be the valence electrons that are in the atom that are going to be shown as being a part of making a chemical bond. When we think back to the stuff about Chapter 4 about ionization energy, how much energy is required to eject an electron, well, that electron that was being ejected then is the one that's held most loosely by the nucleus, and that's going to be the electron in the very last energy level, or the highest one. So whenever you're writing out electron configuration, just find out, all right, well, what was the highest energy level that ever had electrons assigned into it? That's going to be referred to as the valence energy level, and those electrons that are in there, in that level, are going to be called the valence electrons. Those are the electrons that are the farthest from the nucleus, but that are then capable of interacting with other atoms. And so that's going to be where all the chemistry takes place, will be in the valence energy level for atoms that are trying to make a bond with one another, whether that be ionic or covalent. And then just remember, there's no rule that the electrons from each atom has to be on the same energy level. Of course not, okay? You can have all kinds of different combinations then, okay? Now, in doing these Lewis structures, then we have several ways that we can show these electrons, and so just sort of some kind of a hieroglyphic. So we use dots. You may have heard them referred to as Lewis dot structures. Your book calls them that, Lewis dot structures. Open circles, asterisks. I've seen people use asterisks, plus signs. I mean, it doesn't really matter. Just some sort of symbol that would then represent the electrons. If you're doing an ionic compound, then what we want to do is to show how those electrons are actually being transferred from the metal to the nonmetal. Remember, doing your ionic bonding formulas, compounds in lab, how that you have a metal, which forms a cation, so he's going to be losing an electron, and then you have the nonmetal, who's going to be making the anion. Well, he's doing so because he's then taking an electron. So think of ionic bonding as being engaging of atoms by transferring electrons from the metal to the nonmetal. And then see, that's how the ionic bond is formed then, because once those ions form, then the 2 ions will stay together because they'll because of the attraction of oppositely charged ions. So that's why they don't just go on their merry way. You know, if one atom loses an electron and that's what he really wanted to do, and another atom gains an electron, why don't they just go on their merry way? Well, it's because the positive and the negative charges are going to be holding those guys together, and that's how you make an ionic bond. When we do the covalent compounds, then we're going to use dashes. When we do covalent compounds, we're going to do dashes. Those are the ones that you made in lab, writing the formulas and things, where they were covalent molecules because they consisted of all nonmetals, and then hydrogen can also be included there because hydrogen's not really a metal. He's just in group 1 because of his electron configuration, 1s1, but he's not really a metal. He actually bonds covalently, and it's really due to the fact that his electronegativity is 2.1. Remember in chapter 4, electronegativity scale goes between 0 and 4. So he's halfway across, a little more than halfway across the scale. That means he is an element that is capable of sharing and not just simply losing electrons like the rest of his non-metal or metals that are in group 1 then. Okay. Now, as we go through this, when we get to the covalent ones, there's a handout that is going to be a step-by-step procedure that we'll use to draw Lewis structures. It's a handout that is from section 6.3 in your textbook. So again, in the news item specifying, all the things that you want to have handy, periodic table, that Lewis structure, step-by-step set of instructions, and then of course this handout here that you could refer to as I go through it. That's going to be for the covalent ones. Now what we want to do first though is just look at ionic compounds. How do you draw a picture of how the ions are actually formed in the making of an ionic compound? And for that, you don't really need that step-by-step set of instructions. It's only going to be for the covalent ones that we're going to be using those for. So let's start with just one simple rule to remember as we go throughout the whole thing here, is that when you look at the group number, that group number, the Roman numerals, except for the transition metals, of course, but any of the A groups, when you look on the Roman numerals of the headings on your periodic table, what's wonderful is that that's the number of valence electrons that that particular atom would have. The other way that you could figure that out, of course, is you'd write out the electron configuration, go find out what's your highest energy level that ever had electrons in it, add them all up, and that would tell you how many valence electrons it has. This makes it much easier by just simply looking at the group number, and that'll tell you your valence electrons. Okay, so for ionic compounds, bonds formed by oppositely charged ions, the things that you've been doing in lab. You have a metal and a nonmetal. Okay, now notice I also put in parentheses, nonmetals are going to obey the octet rule. The word octet, literally translating into 8, okay, means that all of your nonmetals then in your Lewis structure are going to have 8 valence electrons, or 8 little dots or circles or whatever we use to represent the electrons. It's going to always have 8 electrons drawn around it, okay? You don't see that for the metals, just because remember that what they're doing is they're losing valence electrons, but for the nonmetals, they're going to be gaining electrons, and so you're going to have 8 electrons show up. That's because that 8 valence electrons, that is the valence configuration of the noble gases. So that is what all of the elements are trying to become. You probably have alluded to that. Your lab instructor probably alluded to that when you were doing your compound naming and writing formulas, is that, everybody in group 1, lithium, sodium, potassium, those guys all form +1 ions. Remember that handout from chapter 5 that I hope you've been using, that it lists everybody in group 1 as being a +1 ion. Well, see, now we know why, is because when they lose 1 electron, and they have low ionization energies, so it's not a problem. When they lose 1 electron, that makes them then isoelectronic. Isoelectronic, meaning to have the same electron configuration. When they have that same electron configuration as one of the noble gases, it makes them stable. What we find in nature is that under normal circumstances, having those 8 valence electrons, 2 that would be in the s orbital and 6 in the p's, you can confirm this, work out the electron configurations for any of the noble gases, except for helium, right? That having 2 electrons paired in their s orbital, remember, they all have an opposite spin, so having a set of spin-paired electrons in the s orbital in the valence energy level, having a complete set of 6 spin-paired electrons in the p orbitals, that's a stable configuration. How do we know that it's stable? Because those gases then, those elements, those noble gases, they don't make compounds. They don't interact with other elements. But all the other elements do interact with one another in specific ways in order to make compounds. And the way that they do it is that they're all trying to become isoelectronic with a noble gas configuration. So that's why in group 1, all those guys in the alkali metal family, lithium, sodium, potassium, right? You just count back 1 space on the periodic table, just 1 block. That's signifying like you're losing 1 electron. Hey, that'll be why those guys are going to be isoelectronic with a noble gas by doing so. So let's take this first, let's take it a simple example like NaCl. So if you look at Na's configuration, right, have your periodic table, he's going to be neon, and then, get my pen to work here, 3s1. And then if you look at chlorine, he's going to be neon, 3s2, 3p5. So now here's going to be the beauty, is that that electron from the sodium is going to be transferred to the chlorine. That's going to then make the chlorine be 3p6. Yay! That means that he is now isoelectronic with argon, but that's going to then make him a chloride. Remember, you're using those IDE endings? That's going to make him a chloride ion, and then by that sodium having transferred, get it? The ionic idea is that it's a transfer of valence electrons from the metal to the nonmetal, that he now is going to become then a positive charged ion. So you have a cation and an anion. And then, of course, the reason why the formula was going to be NaCl, one sodium ion and one chloride ion, is that your charges then were going to add up to be 0. So you had a +1 charge and a -1 charge, and that added up to be 0. Remember, when you're writing your formulas, do your little crisscrossy thing to get your subscripts. All the charges of the ions had to add up total to be 0. The total number of electrons being lost or transferred by the metal or metals are being given to the nonmetals, and that has to be the same. Okay, now, that's not the Lewis structure, but let's draw the Lewis structure now, meaning that we want to draw a two-dimensional picture showing how this happens. Okay, so what I'm going to do is I'm just going to draw a big Na, leave a little bit of space, and then draw a big Cl. In other words, look at the definitions up the top, or the little checklist is you use the chemical symbols of the elements that are in the molecule to represent the nucleus and all the core electrons, because they're not the ones that are really going to be doing the chemistry here. Then I put in dots or circles or whatever to represent the valence electrons. So for a sodium atom, he's in group 1, and so he's the group 1 number represents the number of valence electrons. He has 1 valence electron. We already know that because if you work out the Lewis electron configuration, it's neon 3s1, so he's got 1 electron in his third or highest energy level. So what I do is I draw then a dot in between the two chemical symbols. Whenever you have dots that are going to be in between the two chemical symbols, that's going to be the area where you're saying that those electrons are actually involved in making the bond. So that's going to be the place where you're saying those are going to be the bonding electrons, the ones that are actually involved in doing the chemistry. Okay, now, what he's doing, though, is remember, is that sodium is actually going to be giving that electron, transferring that electron to the chlorine. So I draw an arrow signifying that that electron then is not staying with the sodium, but that is being given or being transferred to the chlorine. So then sodium is going to now have a positive charge because he's lost his electron. Okay, now for the chlorine, he has 7 valence electrons. You can go to the periodic table, right? See that chlorine's a halogen in group 7. He has 7 valence electrons. We already know that because when you look at his configuration, we just did it, neon 3s2, 3p5. Notice third energy level is the highest one that shows up in the configuration, and there's 2 electrons in the s orbital, and then there were originally 5 electrons, so that's a total of 7. So now what we're going to do is I'm going to show those 7 electrons then with circles just so that you can tell the difference when you come back and look at this later. You can tell the difference between which one was the sodium valence electrons and which ones were the chlorine valence electrons. I'm going to use a circle, and I'm going to put one and pair it up with that electron that's coming over from the sodium. And then I'm going to put in the remaining 6 valence electrons in pairs and just arrange them around the symbol of my chlorine atom. And typically the protocol is that you would put 2 at the top, 2 on the sides, or have 2 on the sides and then some on the bottom. It kind of makes it a little square. That's just sort of like aesthetically pleasing, okay? Sometimes we even have more electrons, so then it's sort of like you're putting them in on the corners of a square, but essentially, you know, top, bottom, and sides, you'll have electrons, okay? Now, remember that chlorine was accepting that electron, the valence electron from the sodium, so now he has an electron that he didn't have originally. That makes him having more electrons than he does protons, so he's an anion. And then, of course, that's what makes the ionic bond. So there is then the complete answer then to the Lewis structure for a sodium chloride molecule or formula unit of the ionic compound. Those electrons, the one that's the dot and the ones that the circle in between the two chemical symbols, those are called the bonding electrons. These guys that are out here, these other 3 pairs that are out here, These are classified in one of two ways. You could think of them simply as being the non-bonding electrons. Go figure. Finally, chemistry might actually make sense, right? Is that you have electrons that are involved in making the bond, so we call those the bonding electrons. Those are just the ones that are in between the two chemical symbols. The ones that will appear then outside, or the external area of an atom, those are going to be called the non-bonding electrons. But the ultimate phrase or terminology that we all use in chemistry is that we call those guys the lone pairs. We call them the lone pair electrons, or LP for short. So you'll see that I'll be calling those guys the LPs, or the lone pair electrons, all the time then, okay? Now, what's that business about the octet rule? The nonmetals, so that's the chlorine, count up all the electrons that are drawn around him, including the one that he's received, of course. You count the one that's been received from the sodium. That chlorine has 8 electrons. Those electrons then, 2 of them are in his s orbital, and then see, by gaining the 1 electron from the sodium, he went from being 3p5 to 3p6. That now puts 2 electrons then in each of his 3p orbitals, thereby making him isoelectronic with a noble gas, argon, and then sodium, by losing 1, he becomes isoelectronic with neon. Okay, so that's the idea of the octet rule, is that you'll actually physically see 8 electrons, 8 valence electrons, circles, dots, whatever, around your nonmetals. You don't see it around the sodium, but think about it, the sodium really, truly is obeying the octet rule as well, because when he loses that 3s1 electron, let me go back up and circle, what's left to his configuration? Just neon. In other words, it's the same as the configuration of neon. And of course, the neon's configuration then in the valence energy level is 2s2, 2p6. So they all are obeying the octet rule. It's just that the only ones that you physically see 8 electrons drawn in the Lewis structure picture is going to be only for the nonmetals. All right, now that was a nice one where you just simply have 2 atoms that are going to be trying to bond with one another. So let me add a page here and show how that, let me show now what happens if you had just a little bit more complicated of an ionic molecule or compound. In other words, what if the subscripts weren't just a 1-to-1 ratio between those guys? So take, for example, what if I had, say, calcium bromide. Try to pick something that would be fairly similar to the one that we just did. Okay. Now the issue is going to be first here is that, see, I have 3 atoms, or eventually they'll be ions, but I have 3 atoms instead of just 2, so I can't just simply draw them side by side. For this, you do have to think, okay, well, what are each of these chemical species going to be doing? Well, the calcium's the metal, so he's the one that is going to be losing electrons. How many electrons? Well, on the periodic table, he's in group 2. Those guys all form 2+ ions, and the reason they form 2+ ions is because they have 2 valence electrons, and when they lose those, they're going to be isoelectronic with a noble gas. Calcium with 20 electrons, he loses 2, now he's got 18. That's the same as argon, so he's losing that 4s2 when you look at his configuration. The bromine, though, can only take 1 electron, right? When you look at the bromine in the halogen family, group 7, he has 7 electrons, he needs 8. That's only 1 electron away, so he's going to be wanting to become isoelectronic with krypton. He only needs 1 valence electron. So he can only take 1, but the calcium has 2 to give away, and you got to make them both happy. Number of electrons lost is the same as the electrons gained. That's why you were writing those formulas then in lab as CaBr2, that he had 2 bromines because he can only take 1 electron apiece, but the calcium has to give away 2. Well, so let's just draw the picture then. Exactly what I just said is that you have a calcium then that needs to lose 2 electrons. He'll be giving 1 to a bromine on the right, and then I could just put the other one on the left. Just kind of put him in the center and then flank him on either side by the bromines. He'll be then losing 2 electrons, and now he'll have a 2+ charge. The bromines are now going to be bromide. The 2 hydrogen atoms, they'll approach one another. And in so doing, their s orbitals are going to overlap with one another, sort of like doing those little Venn diagrams. Remember doing those in algebra? when there is a region of where their s orbitals are going to overlap, that's going to cause then both of those electrons to essentially be occupying a region of probability then for both hydrogen atoms at the same time. Well, so they still have some probability, these areas that I'm shading out here. There still is the probability that you would have electrons out there. But what is really going to happen then is that you would have, let me just use these two dots as being the nuclei, is that you would then have the greatest probability of both of those electrons then being in between the two nuclei, thereby occupying both of the s orbitals at the same time. That's called making a sigma bond. Make an S here. That's called a sigma bond. Okay. Now, it's also referred to as a sigma overlap. In other words, it's showing how that the orbitals are overlapping with one another. This is a part of what's called valence bond theory in Chapter 7. It was hard to talk about Chapter 6 just by itself, and vice versa. That's called a sigma bond, where the two orbitals, the way in which the two atoms will make a covalent bond with one another is that they just simply come and approach one another. And in overlapping, we're essentially then saying, all right, well then both of those valence electrons are belonging simultaneously to both atoms at the same time. Now, instead of using dots all the time with covalent Lewis structures, what you'll see that we're going to do is we're going to draw it like this, where the electrons that are being shared, in other words, the bonding electrons, remember anything that's in between the two chemical symbols are called bonding electrons, we're going to call those shared electrons, or we're going to draw them, I should say, with a dash, sort of like it's a toothpick or some kind of a rope that is showing that those guys are attached or connected with one another. Lone pair electrons, if we have any, we don't here in this H2, all we had is just the original 2 electrons, but if you had lone pairs, you would put those as dots still, but you could do dashes just simply for the electrons that are going to be shown as being shared electrons, okay? Now, the step-by-step process that is in your book on Table 6.3, that handout that I included for you to download and have ready looking at this, it's not really necessary to think of having to do all those steps here for just something simple like a hydrogen molecule, but nonetheless, you could follow the checklist of steps in order to do a molecule as simple as hydrogen. What I'll do is let me do a couple of more just simple molecules explaining how they're going to share the valence electrons, and then as we start to do some of the more complicated ones, I'm going to be referring to that little checklist of step-by-step instructions for how to do covalent molecules. Okay, so let's do another simple one here. And again, pasted some pictures from your book. Think about a fluorine now this time. With fluorine atoms, you're talking about having a configuration of helium and then 2s2, 2p5. Okay, so 2p5, there's the empty spot. We want that to be 2p6, so there's the empty slot that they'll all have then one unpaired electron. Think about how those 5 electrons are distributed into the p orbitals. 1, 2, 3, 4, 5. There's the p orbital then that only just had the first electron. There's the one that's empty. Well, so what that's going to essentially be then is that I'll have a p orbital from one fluorine atom that will then be approaching and overlapping with a p orbital from the second fluorine atom, and then there again it's going to be that high probability then in between the two nuclei where then each of those p orbitals will be overlapping so that this electron from one fluorine atom and then the one from the other one, they belong simultaneously to both of them so that they both essentially then are 2p6, but nobody gained or lost. That's what's making all these guys covalent, is that there are no charges. Nobody lost electrons, nobody gained. They're just sharing the electrons, and so therefore they complete their configurations by sharing, but nobody actually took or lost an electron, okay? So now when you look at the periodic table and you see how that fluorine has 7 valence electrons, well, so they're going to be sharing then one electron with one another. I'm just going to immediately draw a little dash. Each dash is going to then represent what's called a single, get my I in there, that's called a single covalent bond, and it means that they were sharing 2 electrons. we're going to see some here after a while called a double covalent bond, whereby which they're going to share 4 electrons, or we can even have triples, just like baseball, single, double, triple. They can have atoms that would share 2, 4, or 6 electrons, and there's no rhyme or reason as to how you could predict that ahead of time until you've gained enough experience and you can kind of make some predictions, but you don't worry about it. It will work out the way that it works out. We're just going to follow these steps here in a second. Okay, now for a simple molecule like this, though, 1 electron is going to be shared between each of the fluorines, and then remember they have a total of 7 valence electrons, so they shared 1. That means they each have 6 left. I'm just going to arrange the... Okay, so now let's look at a molecule like water. Now, just like I did with the ionic structure, where I don't have just simply 2 atoms, now I have 3. Now we have to consider what should be the arrangement of these atoms, because I have 2 hydrogens and 1 oxygen. Common sense, or just your intuition, might give you the answer that if you have 1 oxygen and 2 hydrogens, that perhaps what we should do then is to put the oxygen in the middle and then flank it with the 2 hydrogens, just like I did my calcium bromide example, and you would be correct. In fact, we're going to look at that handout here in just a second. You'll see at the very bottom, I also typed in instructions. How do you figure out who your central atom is? Who should you put in the middle? And then who will be all the atoms that are on the outside? Those guys are called the terminal atoms, okay? It's very simplistic from the standpoint that your intuition probably told you that that might be the way that it works. It's because Mother Nature loves symmetry. Even with these covalent molecules where they're sharing electrons, Mother Nature loves symmetry. So you would have then an atom that is going to be in the middle, and then you have more than 1 hydrogen, so just arrange those around it, like doing a flower arrangement or something, that you would then arrange the other atoms around them, okay? Symmetry, so just balancing out the structure, putting the one that you only have 1 of in the middle and then flanking it by the others, that's going to pretty much take care of probably 90% of all the different structures that we do. If it's not as straightforward, then there are other little tricks that we can use. We'll get to those in just a second. But there are other little tricks that we can use to tell you which one should you put in the middle. But this one's fairly obvious that with only 1 oxygen, he should go in the middle, and then I'll make the bonds between the 2 hydrogens. If you correlate that with the information that we already know from the periodic table, you look at the periodic table and see how oxygen is going to move forward 2 spaces or gain 2 electrons, right? That he would then become isoelectronic with neon. It makes sense then to put him in the middle so that he can then share electrons with both hydrogens, because that's what he needs, is 2 more electrons. He has 8 or 6 valence, and so then he's shy by 2. And then hydrogen, he only has 1 electron, and he only ever wants to share 1 electron. And so hydrogen always will be the terminal. He'll always be on the outside, just making 1 bond with each of these guys. Okay, so let's look at those instructions and see now how this is going to help us to figure out our steps. Okay, so this is the handout that I'm referring to. You guys can, hopefully you've already got it downloaded, that you've got it next to you, okay? So I'll kind of go back and forth here and refer to them here in time here. So first thing you're going to do is, in step number 1, from the molecular formula, is that you draw what's called the skeletal structure. So that's what I was just referring to here, is that you figure out how should you do the arrangement of your atoms, and you're trying to figure out then who the central atom should be. Okay, well, here's going to be the thing that you're going to look for. Down here at the bottom is, first, see if there's just an easy way to make the molecule look symmetrical. So having 1 hydrogen in the middle and then flanking by 2 of the oxygens. Now, if that doesn't work, we'll see this happen in just a little bit, but if that doesn't work, then you ask yourself, which one of the atoms in the molecule needs to share the most? Not who has the most valence electrons, but who needs to share the most. So I already said with oxygens, he has 6 valence electrons, he's in group 6. So he's 2 electrons away. 8 minus 6 is 2. He's 2 electrons away. If you look in the periodic table, you could move forward, count over 2 blocks from oxygen over to neon. He needs to gain, going forward, he needs to gain 2 electrons. And so then he's going to be the one that needs to share the most, because hydrogen then, he only has to go over 1 space from block number 1 to block number 2. From hydrogen to helium, from hydrogen to a noble gas configuration is just 1 electron. So therefore, oxygen's the one that needs to share the most. Now, the instructions that are on this list here from the book, they talk about then looking for the least electronegative atom. So you go back and think about chapter 4, how that the electronegativities of the elements, they increase as you go over to the right and up. And so oxygen is farther to the right. He's actually more electronegative than hydrogen. I actually just suggest that you kind of forget about that and do the steps that I've got here. Do symmetry first. Can you just make the molecule look balanced by the number of atoms of each kind that you had? Then if that doesn't work, then look to see, all right, well, whoever needs to share the most should go in the middle. Last but not least, if all those other 2 things fail, and so you shouldn't need this one too often, if then that all else fails, then you look for the one that is the least electronegative atom, and that'll be the one that you put in the middle. Now, notice what I'm sort of indicating here is that you're always going to have one atom that's in the middle, and then you're making your bonds. I mean, how many ever bonds you're going to end up making, that you're making your bonds then to all these other atoms on the outside. Think of it as being like spokes of a tire, or of a bicycle tire, or a wagon wheel, okay? You're going to have a central atom, and then the ones that are on the outside bonding all to the middle, the spokes, okay, those guys are going to be referred to as the terminal atoms. Okay, so in the first rule there, it just simply says you're going to set up your skeletal structure and then draw a single covalent bond. You know that by these atoms sharing valence electrons, well, they at least have to share 2, right? So we're going to go ahead and we're going to draw then a single covalent bond, a dash, between the central atom and then each of the surrounding ones, okay? So that's what we'll do here in our structure. Let me squeeze him down. We do that in our structure here, so I'm going to make a single covalent bond between the central atom and each of my atoms. Okay, that's done. Okay, step 2. Count the total number of valence electrons present. Remember that the element's group number gives the number of valence electrons. It contributes to the total number. When we have polyatomic ions, we'll do some of these guys here in a second. Okay, you guys were supposed to talk about that in lab this week. You will indeed now have to just look at those 2 videos and the handouts that I gave you on D2L in the news item, that you would add electrons or take away if you had a negative ion or if you had a positive ion. Okay, we'll do some of those here in just a second. Okay, so now I'm going to go and figure out my valence electrons. All right, well, for an oxygen atom, that's 6, so oxygen has 6. Hydrogen has 1, but there's 2 of those guys, so that's really a total of 2 electrons. That means that I have then 8 electrons to work with in my structure. Okay, so you look at the group numbers. Oxygen's in group 6, so that's 6 valence electrons. And then hydrogen in group 1, that's 1 valence electron, but there's 2 of them, so that's a total of 2. 6 and 2 means I have a total of 8 valence electrons to work with. Okay, now, rule number 3, get it in between my markings here. For each bond in the skeletal structure, remember we already drew single bonds? Okay, for each of those, subtract 2 electrons from that total that we just calculated, and that's going to determine how many electrons still remain in the structure that we'll have to put in. In other words, those are going to be the leftovers, the lone pair electrons that we're going to have to put in. Okay, so let me get that out of the way. We had 8 valence electrons, right? So then I've used up already. There's 2 and there's 2 for my single covalent bonds. So subtract 4, that leaves me with then 4 electrons left over to put in as lone pairs. Now, the lone pair situation here, you always have to remember to do it in the exact sequence that is specified here, okay? In step 4, let me move this out of the way just a little bit. In step 4, hopefully you can see this, the remaining electrons, you will complete the octets of the terminal atoms first, the ones that are the spokes, the ones that are on the outside, okay, by placing pairs of electrons on each. But here it is in this one, for this molecule. Remember, the H atom only requires 2 electrons to complete its valence shell. Therefore, you never, ever put lone pair electrons that you might have extra on a hydrogen. The single covalent bond that he's making is all he ever gets. You never, ever put lone pair electrons on a hydrogen atom, okay? If we have more than one type, we don't have that here. Both of our terminals are hydrogens, but if you had more than one type, then you have preference given to whichever is the most electronegative element or the more electronegative element, okay? So now, when I look at my water structure, get him out of the way. Well, I'm going to try to get him out of the way. There we go. Okay. There we go. I had 4 electrons, right? I had 4 electrons that I needed to fill in. None of those are going to go on the hydrogen. I don't put any electrons on that hydrogen, okay, because they're all octets are complete by having the single covalent bond. So that means all 4 of those electrons then are going to go on the oxygen. So let me put 2 there and put 2 there. Remember, everybody's always in pairs. You will never have a single electron by themselves. Everything is always going to be in pairs. So that gives me then my complete Lewis structure for a water molecule because everybody's octets are completely obeyed then. Hydrogen, it's not really an octet, it's just the 2 electrons, okay, so he's okay. The oxygen then, he now has 8 valence electrons, right, because he has 4 electrons that were involved in bonds, and then he has 4 electrons that were involved in lone pairs. So that would be my complete Lewis structure then for a water molecule. Now let's try a molecule like oxygen. We'll get to see another kind of a scenario here. So again, back to a molecule that's fairly simple in order to figure out the arrangement. There's not really going to be a central atom. There's just 2. So we would just simply draw the 2 oxygens next to one another. Okay. Then, following our little rules, our little checklist, let me pull that up here just again. All right. Step number 1, we got the skeletal structure, okay, just the 2 atoms right next to one another. And then we're going to draw a single covalent bond. This is all in step 1. Draw a single covalent bond then between the 2 atoms. So I'll draw a single covalent bond between my 2 oxygens. Okay, next, remember, step number 2, go get and figure out how many total valence electrons we have. And then after that, we're going to subtract, kind of do 2 and 1 here, subtract 2 electrons then from that total for every one of those single covalent bonds that we had put in. So for our structure here, that's going to be then 6 valence electrons for oxygen. He's in group 6. There's 2 of those guys, so that's going to be a total of 12 electrons. I've used up 2 already, so that means I have 10 more electrons to place in my structure. Okay, so then remember, step number 4, I'm going to use remaining electrons in order to fill in the octets of all the terminal atoms, which here everybody's the same. There's no central versus terminal. So 10 electrons. All right, well, so now remember, the one bond that's already in between these guys counts as 2 electrons. To obey the octet rule, then these guys would each need 6 more. So there I use 6 just on that left-handed oxygen. There's no rhyme or reason why to use that guy. Okay, that then is going to leave me with just 4 left over. So I started with 12, used 2 for the bond. That left me with 10 to put in as lone pairs. I just used up 6. So now that leaves me with only 4. Well, so now the left-handed oxygen has his octets okay. He's got a total of 8, 2 for the bond, and then 6 for the lone pair, so that's 8. 4 remaining electrons then are going to go to the right-handed oxygen, okay? No rhyme or reason where you stick them. You know, I put them at the top and on the side. You could have put yours at the bottom and the side or whatever, okay? Now we recognize that the left-handed oxygen is okay, but the right-handed oxygen is not. It's only got 6. 2 for the bond, you get to count those, and then you have 4 that are in the form of lone pairs. So he's only got 6 electrons. Now's when we're going to need then this next rule. Okay, if you have, step 6, if you have fewer than 8 electrons after completing steps 1 through 5. We skipped number 5 because we didn't have any electrons left over. We're not going to need that one for just a second here. We didn't have, after we had completed everybody's bonds and octets, we didn't have electrons to go. We ran out, okay? So step 5 we didn't have to do. Step 6 then, we do run into this. If you have fewer than 8 electrons, then you're going to move 1 or more pairs from a terminal atom to then form multiple bonds to the central atom. Now this one, it doesn't have a central atom, of course, it's just the 2 side by side, but the concept is the same. In other words, what I'm going to need to do is move the lone pairs. This is really the strategy going on here, is that you remove, or you do a move of a lone pair to become a set of bonding electrons, or a bonding pair. Just switch what its identity is. Move it from being on the outside of the symbol to being in between the 2 chemical symbols, thereby calling it a bonding set of electrons. Well, now notice, I'm not going to do anything with the lone pairs on the right-handed oxygen. I'm going to leave those alone because simply moving those in between the 2 chemical symbols and having them also shared with the other oxygen doesn't do anything for that right-handed oxygen. All that would do is then make my total go higher for the left-handed oxygen. So the solution will be is take one of these lone pairs. I'm just going to choose these here at the bottom. It doesn't matter. Again, no rhyme or reason as to why. I'm going to move those guys from being a lone pair then into in between the 2 so that they become a shared pair. So now the Lewis structure, I'm going to get rid of this guy, if I can, try to, okay. I'm going to move that lone pair, and now it's going to look like this. I'll have 2 sets of electrons being shared, and again, every time you do shared electrons, you use the dashes. This is just for covalent structures. And then let me draw in the lone pairs that I didn't do anything with. So those were left alone, and then these guys over here, they were left alone, okay? So I've got exactly my Lewis structure then for my oxygen. Need to get rid of that little blip there. Oh, no. Sorry, pause. Okay, just redrew it. That now I've got this as my Lewis structure of my oxygen, where now I've got a total of 4 electrons being shared. All right, well then that's called a double bond, or a double covalent bond, because now it's going to be sharing 4 electrons instead of just 2. Okay, next one. We can kind of maybe go through these a little bit faster. The more you do, just looking at those little list of steps in the table, 6.3 that from the handout, that we can go just a little bit faster then with some of these guys. So my next one here, I've got 2 nitrogens. Again, he's another one of those diatomic elements. Okay, so I first draw my skeletal structure. Step 1, draw a single covalent bond. Okay. Now, step 2, go count my number of valence electrons. So I have nitrogen in group 5, but of course there's 2 atoms of nitrogen, so that gives me a total of 10 electrons to play with. But I've already used up 2 in making my single covalent bond, so that leaves me with 8 electrons still to put into my Lewis structure. So I go now, step 4, use remaining electrons to complete the octets of the terminal atoms. There's not really a terminal atom, but so what I could do is I've got 8 electrons, maybe like give that right-hand guy 4, and then give the left-hand guy 4. Okay, so that means I've used up all 8 of them. Okay, so when I look at my structure now, though, I recognize then that I've only got 6. When I look at each of these guys, they only have 6 electrons right now. They still need 2 more. Well, then this is where we invoke that step number 6. If the central atom, again, these aren't really central atoms, but we have an atom that has fewer than 8 electrons move one or more pairs, lone pairs, in order to form then what are called the multiple bonds. In other words, you're just switching them from being a lone pair into a shared pair of electrons. So take this pair and move that in. Notice how that's not going to help my left-handed nitrogen, because it would still be counting for him, so he would still be at 6. But what that will do is it'll give that right-handed nitrogen then a total of 8 electrons, okay? Well, so we got to have the other guy then help the other guy out. So let's have him share 2 more. That doesn't affect him, the right-handed nitrogen, just because he's switching from lone pair to shared pair. Doesn't hurt him, but by sharing 2 more electrons, that'll help the left-handed nitrogen. So that now my structure will look like this. I'll have actually then 6 electrons being shared. That is then going to be called a triple bond because it was sharing 6 electrons, just like baseball. Okay, next let's try HCN. Now we have a molecule where I have 3 atoms, but they're all going to be different, so there's not really symmetry that's going to help us on this one because they're all 3 different ones. So one thing to keep in mind is that a lot of times the way in which the chemical formulas are written are giving you a hint as to actually how they're connected together. So for this one, it's really not going to be a big stretch to think that with the way that the formula is written, that it must mean that it's the hydrogen that is then going to be bonded to the carbon in the middle, and then it'll be the nitrogen. So the central atom is going to be a carbon. Keep in mind, though, that our little list of rules down at the bottom, how to choose the central atom, number 1, symmetry, that doesn't work because there's nothing symmetrical here. It's all different atoms. But that number 2, which atom needs to share the most? Well, so you look at the periodic table and again think about the electrons, how they want to become a noble gas, or become the configuration of a noble gas, is that hydrogen will need to share 1 electron so that he can be 1s2. A carbon, his configuration, he is helium 2s2, 2p2. He needs 4. You go forward, count over 4 blocks, go from carbon and then get him over to neon. That's 4 spaces. He needs to share 4 electrons to become isoelectronic with neon. And then nitrogen, he has 5 valence electrons, right? Well, if you count forward to get him over to neon, he only had to go over 3 spaces. He only needs to share 3 electrons. So it's actually rule number 2 then for us on how to determine the central atom that's giving us confirmation that this really will be the way that it works. Carbon needs to share 4. He needed to share the most. He should go in the middle. Okay, so step number 1. I got my skeletal structure, put in single covalent bonds. Now go find out how many I have. So hydrogen's got 1 valence electron, carbon's got 4, nitrogen's got 5, so that's going to be a total of 10 valence electrons. Now I already used up, though, 4 for my single covalent bonds, so that really then only leaves me 6 electrons left over. Now here's then where you have to be careful. You're filling in these extra electrons as lone pairs on the terminal atoms first. You don't do anything with the central atom just yet. Now we indeed do have a central atom. You do the terminal atoms first. Well, so how many of those 6 electrons are going to be given to the hydrogen? None, because you never, ever have lone pairs on a hydrogen. The 2 electrons making that single connection, that single covalent bond to the carbon, he's already then 1s2. He's already isoelectronic with the helium. So that means that the nitrogen then is going to get all 6 of them. And he'll get all 6 because with his single covalent bond, he only had 2. So by giving him then all 6 of those, now that terminal atom, the guy on the outside, the spokes to the wheel, he's going to be then now obeying the octet rule because he's got 8. So now, last but not least, step number 6 in our checklist of how to draw Lewis structures says, what if your central atom doesn't have enough? And it doesn't. The carbon's only got 4, right? The carbon needs more. Well, so then what we'll do is we'll take some of these lone pairs and change them into shared pairs. That's all you do. Just bring those guys in. And so now, not going to let me do it. All right, I'm just going to redraw it. This is the structure that we had originally. of stuff here. I'm going to move 2 of those pairs in. And now we're going to be left with, there we go, having trouble with my pen here. Now we're going to be left with this. Okay, so I have a single covalent bond between the hydrogen and the carbon, and then now we have a triple bond between the carbon and the nitrogen. Okay, so the carbon only had 4 electrons, he needed 4 more, so I took 2 lone pairs. That was me taking 2 lone pairs then off the nitrogen. Let me make them bigger. 2 lone pairs then being brought in to be changed from lone pair electrons into shared pairs, bonding electrons, and so then I'll have this. Now, I've still got my 8, just because I moved them from lone pairs to shared pairs, they still counted on that nitrogen, so he's still got his 8. But then now my carbon has 8, because he has a total of 4 dashes, and each of those are 2 electrons. A single and a triple, he's got 8 valence electrons as well. Okay, next one then, carbon dioxide. So again, symmetry is going to help us here. You only got 1 carbon and 2 oxygens, so just symmetry will be setting us up to put the carbon in the middle, and the oxygens then will be the terminals. Going to have then a single covalent bond in between the 2. Going to have 4 valence electrons for carbon. Going to have 6 electrons, valence electrons for the oxygen, so that's 2 of those though, that's 12. So I got a total of 16 electrons. I already used up 4 of them, though, making those 2 single covalent bonds, which means then that I've really only got 12 electrons to go for my Lewis structure. So you fill in the valence electrons then for the terminal atoms first. This is step number 4. Use the remaining electrons to complete octets of the terminal atoms by placing pairs of electrons on each atom. Complete the octets of the most electronegative atom first. Well, they're both oxygens, so there's no problem there. Okay, so put those guys in. Well, 12 electrons, that means I could give this left-handed oxygen 6, because he only had 2 for the bond. He only had these 2, so if he has 6 more, that would complete his octet. That works out perfectly then that I could give the right-handed oxygen then, and there's no reason why I had to do left first and then right. You can do whatever you want. That I complete then giving him 6 electrons. Now I've used all those guys up. But then, like before, step number 6, my central atom only has 4. I need to have a total of 8. So kind of sticking with sort of symmetry kind of ideas, well, why don't you just like take one of those guys in and then have him do the same thing over here. And then what you'd end up with is this. And you can take any pair of electrons from being a lone pair and turning it into a bonding pair. You can do whatever you want. I just happen to take the top pair. There's no rhyme or reason. There's no rule. You could have taken these guys on the sides or the bottom, whatever you want to do then, okay? All right, so then there now I shared an additional 4 electrons with the carbon, so now he's got 8. And so then just that stuff that's in my circle there, that's the answer then. You have 2 double bonds, and then you have the oxygens with 2 lone pairs each. Okay. One other little thing that can happen that's interesting is we'll talk about that rule where it said if you have an ion, you then, in counting up your valence electrons, you have to take that into account. So here's the nitrate anion. This is one of your polyatomic ions. Again, you were going to look at those polyatomics in lab this week, so look at those videos and the 2 handouts about the polyatomic ions and how you have these guys in compounds. So he's an anion, which means that when we do our total, I'm going to end up adding an electron. Okay, so when we count up our valence electrons, having a negative charge just means that I would add then an additional electron to the total. And of course, if it was a 2- ion, then you'd add 2. If it was a plus, then you'd take away 1. You just do literally whatever the charge is supposed to be doing in the formation of that kind of an ion. Okay, so first get my skeletal structure, and again, here it's not going to be so bad because symmetry is going to be the order of the day. You only had 1 nitrogen, so make him like the hub of the wheel, and then the oxygens will be the spokes of my little bicycle tire. So just however you want to arrange them. Okay, and then make a covalent bond. Well, that wasn't supposed to be a hook. That's supposed to be just a straight line. Make your single covalent bonds then between each of your atoms. Okay, now go get my total. So nitrogen, he has 5. Oxygen has 6, but there's 3 of them, so that's going to be 18. And then, because this guy is an anion, I'm going to add 1 electron. Remember, becoming negative meant that you gained electrons. So I'm going to add an electron. So that's going to then give me a total of 24 electrons to play with. All right, 24 electrons to play with, but I've already used 6. I drew 3 covalent bonds, 3 single covalent bonds from the nitrogen out to each of the oxygens. So we've used up 6. That's going to leave us then with 18 electrons left over. Now if you're catching on, you could probably see what's going to happen here. Each of those oxygens have just the 1 single covalent bond to the nitrogen, so that's 2 electrons. They need 6 more in order to complete their octet. So 6 times 3 is going to work out perfectly here, that each of these guys then is going to get 6 electrons. 6 times 3 is 18, so give him 6. Give this guy 6, and give this guy 6. And remember, you always complete the octets of the terminal atoms first. That's a big mistake people make. They start worrying about, well, the central atom doesn't have enough. You're going to take care of that right now. You do the electrons for the terminal atoms first. I didn't have any electrons left over. We used up all 18. So now, yes, we go and we look at that nitrogen and we see how that he's only got 6 electrons. So I'm going to have to take a lone pair from one of the oxygens and bring it in to be then a shared pair. And I'm going to end up then having a Lewis structure where I'll have then a double bond between these guys, and then these guys will then stay the same. If I bring that set of electrons into the nitrogen, that's going to make it look like this. I guess I took the top one, so let me do the sides here. Okay, and then we had 1 more oxygen down here. Okay, so I brought that lone pair that used to be up there, I brought it in to be shared with the nitrogen. Okay, now the other convention then is that we also then just take the entire structure and put brackets around it, and then we say that the charge of the entire thing then is a -1 charge. You don't have to specify exactly which one of the atoms is really the one that's bearing the -1 charge, okay? It's a little bit more complicated than that. We just say put the whole ion in brackets and then put the charge next to it, because then that's going to represent that somewhere within the Lewis structure that there is an extra electron that was gained that it didn't have originally. Now the thing that you might notice is I took the lone pair then off that left oxygen and moved it in to be shared to create then a double bond to the nitrogen, and then of course the other 2 remained as single bonds. How do you decide whether you would have then formed the double bond there, or maybe we should have taken in one of these lone pairs and then made the double bond there? Or what if you took the lone pair and made the double bond there? The answer is that there are actually then 3 possibilities for the Lewis structure. That you may have brought in the extra lone pair and formed the double bond there, and then these other guys would just be left alone. This would now be going back to the original dilemma and saying that he would be left alone. And then last but not least, who's to say that it wasn't the bottom one? So I'll take the lone pair off of him. In other words, what I'm doing is I'm just simply choosing in succession different oxygens that will be sharing an additional pair. So wherever the double bond is, it was that oxygen then that took one of his lone pairs and moved it in, because the nitrogen started out, remember, it started out as only having 6, and so then one of those oxygens, this was the original dilemma, one of these oxygens then is going to have to take a pair. Well, do you take this one and bring it in and make the double bond there? Or do you take it from this guy and make it there? Or do you take it from this guy and make it there? Okay, now to get rid of all that, okay. So, the answer is all 3 are possible. And the real or the true Lewis structure of the nitrate anion then is a combination of all three. One of the disadvantages of writing Lewis structures is that it gives us this idea that the electrons are static, that they really are like just staying in place. We don't want to ever forget that the electrons are moving all throughout the entire ion or molecule. And so it's as if that extra electron or that bond that is a double bond, it's really happening between all three atoms simultaneously. We'll say it's really like a 1 1/3 bond. It's like that extra bond is being shared simultaneously between all three of them. Okay. Well, all three of these Lewis structures then are correct. Well, so here's what you have to remember then is if I just ask you to draw a Lewis structure, you just draw one of them. However, if I say draw all possible resonance, here's the vocabulary term. If I say draw all resonance forms or resonance structures, that means then that I do want you to draw all of the potential possibilities. So all the choices, taking a lone pair off the left-handed oxygen or the right-handed one or the bottom one. Draw all three possibilities, and that's what it'll always be. You're not moving the atoms around. It's always about what lone pair did you choose to go and be shared to create a multiple bond, either a double or a triple, okay? So you draw all the different possibilities. That's what's called doing resonance. Okay, now after having all those rules, and I got a bunch of them for D2L structures that you can practice, it's on a homework just for basic Lewis structures. Do those before you would go on and try the Connect homework, of course. Try all the ones on D12 first, and so you can check your answers, and then go to do the Connect homework ones, okay? What happens then when we have some molecules and species that don't follow the rules? Like everything else, everything we're describing in chemistry are generic properties or general trends or overall patterns, but there are always going to be little exceptions, I before E except after C. So the exceptions to the octet rule can be summarized just in two ways. You either can have an atom that would go over 8 electrons or you can go under. That's your two possibilities. So the book kind of spells out all these different sub rules and stuff like that, but I'm just going to distill it down for you that there's just one of two things that could happen. You're either going to go over or you're going to go under. Okay, for the ones that go under, for example, if you have a compound like boron trifluoride, okay, if you draw the Lewis structure for boron trifluoride, I'll let you work through the steps. I'm going to kind of just go straight to the structure. Is you have 3 valence electrons for your boron, so it's going to make then 3 covalent bonds to the fluorines. Fluorine has 7 valence electrons. He shares 1, and as hopefully you've started to notice, the halogens typically have a pattern with them. They share 1 electron to make a covalent bond, and then they have 6 more electrons to go as lone pairs, and then they're all going to obey the octet rule, except for the boron, the central atom. The exceptions are only for the central atoms here. All the terminal atoms, all the ones on the outside, must continue to obey the octet rule. There's no evidence that they don't. But for the central atom, if it's an element like boron, and the only ones that are seen to do this are elements that are in group 3A, and so with covalent compounds we're essentially just talking about boron, is that it's actually okay for them to have less than the 8 electrons for the octet. So it's called an incomplete. It's called an incomplete octet, meaning less than 8. Now the reasoning behind it is, remember that what we would do when you look at the checklist, the step-by-steps for how to draw Lewis structures on our handout, step number 6 is if your central atom, we just have been doing it already. When your central atom doesn't have enough, we'll just bring in one of those lone pairs. Oh, and then that could be resonance structures, right? Because you could bring in this one, or you could bring in this one, or you could bring in this one. In other words, you just need to share 2 more electrons with the boron, and then you get something like this. You get a double bond then, so this is going to be very similar to that nitrate one we just did. Okay, so then you're like, hey, that'll be great. Everybody's got 8. No experimental evidence And technology has gotten better. They used to think that maybe this is what occurred, but now the technology has gotten better, both experimental procedures and with computers modeling. There's no way that one fluorine or any fluorine would choose to share an additional, other than just the one that he wants to share so that he can become isoelectronic. There's no way a fluorine would then share an additional set of electrons pair in order to make that central atom happy. And then, of course, there really would be resonance where then the other two could then have an equal probability of doing it as well. The reason why there's no way that could ever happen is because fluorine is the most electronegative element, chapter 4. The most electronegative element meaning he has the greatest attraction for electrons, not for letting anybody else access them. He lets the boron access or share one valence electron because then that's going to make him happy. The orbitals from the boron would overlap with the orbitals from the fluorine. That'll make him happy, but then that's it. It's just one and done, and he's all set. So the Lewis structure is indeed going to be just the one where everybody is a single covalent bond and only has 6 valence electrons around the central atom. It's only going to be the central atom, and it's pretty much just keep on the lookout for compounds that have boron with the central atom. Okay, so then how about the ones that you can go over? So if you go over, these guys are called an expanded octet. More possibilities with these guys. This is going to end up being called an expanded octet. Okay, more possibilities here. You'll see the rule is, or be on the lookout for, nonmetals, again, only the central atoms, but nonmetals that are in periods 3 through 6. And the reason why these guys can go over 8 is because remember that in row 3 on period 3 of the periodic table, that means that you're putting electrons into the 3rd energy level. And what orbital shows up for the first time in the 3rd energy level? The D. So you have the octet rule is 2 electrons in the S and all 6 in the P's to give you 8. That's what the Lewis structures or the configurations are for the noble gases. But in the 3rd energy level, even though starting in the 3rd row of the periodic table, even though we're not putting electrons into them, there are d orbitals that are available for occupation in the 3rd energy level, and so forth and so forth, 4th level, 5th level. Even though they're going to be empty, well, there's room then, potentially, theoretically, right? There's room for 10 additional electrons. So theoretically, you could have, it won't be the octet rule, you go up to whatever the math word for 18 is. Technically speaking, you could have 18 valence electrons then for an atom. That doesn't actually happen. 14 is absolutely the most that I've ever seen. It kind of correlates to the group number. So when you look at group 7, the halogens, 7 times 2 electrons in each orbital would give you a maximum of 14. Even that's kind of rare. Pretty much the 2 exceptions that you're going to be on the lookout for will be 10 and 12. In other words, you go over by 2 or go over by 4 electrons, okay? Again, the idea, everything's in 2s because everything is paired, okay? Well, so here's an example of PCl5 doing that very thing. Again, first you'd figure out your arrangement. Well, so this one isn't going to be quite as pretty. This is going to really look like a wagon wheel or the spokes of a bicycle tire because you'll have your phosphorus by symmetry in the middle, and then you're going to have all your other chlorines then being the terminal atoms, so you're making a literal wagon wheel, okay? Phosphorus then has 5 valence electrons. Well, guess what? We essentially have already used them all up because he shared one with each of the 5 chlorines. Chlorine then, he has 7 valence electrons, but there's 5 of those guys, so that's really a total of 35 electrons. So that's 40 that should show up in the structure. I've already used up 10. And that's a dead giveaway, right? When you have a central atom that has 5 covalent bonds already, just by scratching out the skeletal structure, you already know you're up to 10 electrons. You've already convinced yourself that that's a expanded octet. And it's okay because phosphorus is in at least row 3, period 3 on the periodic table. So from row 3 then going down, non-metals, this is all about covalent. This is all about covalent, so non-metals. So I've already used up 10 electrons. That leaves me with 30. Okay, well that's going to be 6 then for lone pairs on each of the 5 chlorines. So the chlorine only has the single covalent bond. These guys then are just going to have 6 more on each, and that's 6 times 5 is 30. So I will have then accounted for all 30 of the leftover electrons. Okay. Again, the idea is that all the terminal atoms, the chlorines, the outside guys, the spokes, they continue to obey the octet rule. The exception to the octet rule is for the central atom, and it's okay because phosphorus is in period 3. So he's able to accommodate more than 8 electrons being shared because he's got d orbitals. In Chapter 7, we'll talk about more what's called the valence bond theory and the VSEPR theory, which helps to explain what is going on with those d orbitals, that it's actually then allowing it to accommodate having more room to make bonds than just simply with the 2 electrons in the s and the 6 electrons in the p orbitals. Okay? For right now, we're just drawing the structures. Okay, let's try another one. How about sulfur hexafluoride? Again, if you look at the formula, and once you scratch out your skeletal structure, that you've got the sulfur in the middle, and then you're going to have 6 fluorines going around him. When you just scratch out the Lewis structure, the skeleton, and get your single covalent bonds, you already know that you're up to 12. So it's going to be obvious that you've already shot past your octet because you've already got 12 accounted for with just the single covalent bonds. So sulfur has 6 valence electrons, and I've already used them all up. Okay, fluorine, he has 7, and I got 6 of these guys. Okay, so that's going to be 42. So that's really then a total of 48 electrons. I just used up 12, right? For each of those single covalent bonds, we just used up 12. So that's going to leave me with 36 electrons. Perfect, because the fluorine only has the 2 for the bond, meaning that he needs 6 more. Each of the 6 fluorines needs 6 more. So 6 for each of the 6, that's 36. And there you have your expanded octet around the central sulfur atom. Last but not least, I did want to let the cat out of the bag and show you how that's very unusual and very, very extraordinary experimental conditions, high pressure, high temperature. Starting in about the early to mid-1950s, chemists were able to actually synthesize compounds with a noble gas. In other words, you're going to force those noble gases with their perfect, their oh-so-cute and perfect configurations, 8 valence electrons, 2 in the s and 6 in the p's, that forces them to share those valence electrons in order to form compounds. So very rare circumstances, but you can actually get them to do it. Okay. Symmetry will help us. We know that the xenon's going to go in the middle, and then the fluorines are going to go as being the terminals. Okay. Notice the selection of the terminal atoms. It's typically going to be fluorine, oxygen, or chlorine as the only choices that can also then help these kinds of molecules to form. In other words, how are you going to force a xenon? How are you going to force a noble gas to be sharing valence electrons? Make a bond under extraordinary experimental conditions with an atom who is very electronegative. So those are your top 3, fluorine, oxygen, and chlorine. Okay, so you're going to have then a single covalent bond between each of these puppies. Okay, so far everything looks normally like, oh, hey, that's 8 electrons. But you have to remember that xenon, he has 8 valence electrons already. That's the whole business of this being the octet rule, is that they already have 8. Therefore, they don't form compounds, except under extraordinary circumstances. Fluorine, then, he's got 7, and we got 4 of those guys. That's going to be 28. So this is a total of 36 electrons that should be in my structure. Now, by making the 4 covalent bonds, then, I've already used up 8. So that's going to leave me with 28 electrons to go. So, 28 electrons to go. The fluorines then need 6 each, okay, because they've got the 2 for the covalent bond. So then they'll need 6 more apiece in order to make their octets. Remember, you just always finish out your octets of the terminal atoms first. Okay, so all the fluorines made their octets. I gave them each an additional 6. But there were 4 of them, so that's an additional 24 electrons that I just now consumed. That leaves me then, this has never happened, after completing the octets, I still have electrons left over. This then is where you're going to have step 5 in our list of how to do the Lewis structures. Step 5 says place any remaining electron pairs on the central atom. So I've got 4 more, and those will go in as lone pairs as well. And then all you got to do is just be real careful. I put them sort of like catty corner. Be careful to not put your dots where it would be in between the two chemical symbols, between an Xe symbol and an F symbol, because remember, anything you draw in between the letters is being signified as shared electrons, bonding electrons. These are not bonding electrons. The fluorine's octet rule's already been obeyed. These are merely lone pairs that are going to go in on my xenon atom. So, gosh, how many electrons then do I have around, valence electrons do I have around my xenon? Well, you have the 8 that were a part of the original 4 covalent bonds, plus 4 more. There's my expanded octet. And is this allowed? 2, 4, 6, 8, 10, 12. Is this allowed? Yes, because xenon is at least in period 3 through 6.